Hi all, welcome to Heights to Fly. Today we are discussing a topic on Euclid's division lemma. It is a theorem to find out problems related to HCF and some other. First of all, we can discuss the theorem. The theorem states that for a given two positive integers, A and B, there exist unique integers Q and R. These are also integers. Satisfying the condition, both of these satisfy the condition A equal to BQ plus R, where the value of R lies between 0 less than or equal to R less than B. Once again, for given two positive integers A and B, there exist unique integers Q and R satisfying A equal to BQ plus R, where the value of R lies between 0 to B. So, we can prove the theorem using an example. Consider example 17 and 6. We can represent the integer. Yes, 17 is larger than R. So, we can represent 17 using this R according to this expression. 17 divided by 6. The value is 2, 12, 5. Here we get the result as 2 and the remainder as 5. So the value of R is 5 and the value of B is value of Q is 2. This value is A and this value is B. So A equal to B into 6 into 2 plus 5. That is R. A, B, Q and R. Let's go to another example. 455 and 42. 455 is greater than 42. So we have to express 455 in terms of 42. 455 divided by 42. Value 1, 42, 3, 0, 35. So 42 into 10 plus 35. Here the value of A is 455, value of B is 42 and the Q is 10 and get remainder as 35. Again, we have to represent the value 42 in terms of 35. So 35 remainder 7 into 1 plus 7. Again this 35 in terms of 7 into 5 plus 75 is equal to 35. So the remainder is 0. Let's show you 7, 5, 35, remainder 0. Okay. We can use this Euclid's division lemma to find out HCF of two numbers. HCF of two numbers. Here we can find out HCF of 455 and 42. How it is? Last non-zero remainder will be taken as HCF. In the last step, there are three steps are there. In the last step, the remainder value is 0. So we have to go to the previous step. In the previous step, the remainder value is 7. The last step, the remainder value is 0. So we can't take it. In the previous value, so we check it to the previous step. Here the value of remainder is 7. So the HCF of 455 and 42 is 7. Let's go to another example. Here we discuss about two examples, 17 and 6, 455 and 42. We go through these steps and find HCF as 7. Another example. One, 2, 5, 7, 6 and 4052. So 1256 is greater than 4052. So we have to represent 5276 in terms of 4052. 12576 divided by 4052. The value is 4052 into 3, 6, 15, 1, 12, 3, 1, 2, 1, 5, 6, 0, 2, 4. The value of Q is 3 and R is 420. 3 into 3 plus 420 is equal to B into Q plus R. Then we go to 4052 and 420. This is the first step. Second step, 4052 equal to 420. Here the value of A is this and B is this. 4052 divided by 420. So the value 9, 2 into 9, 80. Two, 18, 1, 37, 15, 7, 2, 2. So into 9, this value is Q and this value is R plus 272. This Q and R. Again, this one is not necessary. We can go to the other step. This is not necessary. Again, 420 and 272. 420 is equal to 272 into 1 plus 148. Again, 272 equals 148 into 1 plus 124. 148 is equal to 124 into 1 plus 24. 124 is equal to 24 into 5 plus 4. 24 is equal to 4 into 6 plus 0. So we have to find out the HCF of 12576 and 4052, which is equal to the non-zero remainder. Last non-zero remainder. In the last step, the remainder value is 0. So we have to go to the previous step. So the remainder is 4 and HCF of these two numbers is 4. Another example, 420 and 130. You have to represent 420 in terms of 130. 420 divided by 130 is equal to 390. The remainder will be 30 into 3 plus 30. 130 equal to 30 into 4 plus 10. 30 is equal to 10 into 3 plus 0. So the value of HCF of 420, 130 is equal to not 0 remainder. Here the values remain to 0. So take 10. Let's go to another example discussed in the book, which is in example number 2, I think. And the question is, show that every positive even integer is of the form 2q, and that every positive odd integer is of the form 2q plus 1, where q is some integer. Once again, show that every positive even integer is of the form 2q. This is even positive integer, and 2q plus 1, which is odd positive integer, where q is some integer. Consider A as a solution. Consider A as a positive integer and the b is equal to 2. According to Euclids theorem or Euclids division lemma, we know that A is equal to bq plus r. So A is equal to 2q plus r. Here the value of b is equal to 2, so we have to substitute it as 2. 2q plus r, and the value of q is greater than or equal to 0, and value of r is equal to 0 or 1. 0 or 1. So we can rewrite A as 2q and A is equal to 2q plus 1. Once again, A is a positive integer and the value of b is equal to 2. According to Euclid's theorem, we know that A is equal to bq plus r, and A is equal to, we have to substitute the value of b as 2q plus r, and value of q greater than or equal to 0, and value of r is 0 or 1, because by multiplying q by 2 it goes as even integer, and 2q plus 1 which is an odd integer. So we take this value, r is equal to 0 or r is equal to 1. By this expression we can represent all the even and odd integers. That is why this expression. If A is equal to 2q, it represents an even integer. 2q plus 1 represents an odd integer. Both are positive. Hence the solution is proved. A is equal to 2q, which is an even positive integer. A is equal to 2q plus 1, which is an odd positive integer. Hence the theorem is proved. Let's go to another example. And the question is, show that any positive odd integer of the form 4q plus 1, where any positive odd positive integer is of the form 4q plus 1 or 4q plus 3 where q is some integer. So these numbers are odd positive integer. And once again the question, show that any positive odd integer is of the form 4q plus 1 or 4q plus 3 where q is some integer. Here the solution is I have to start with A. Consider A is a positive odd integer. We have to apply the Euclids division lemma. A is equal to bq plus r and the value of b is equal to 4. And the value of r lies between 0 and 4. So r can take values 0, 1, 2 and 3. We can write using this value A as 4q plus r. Here the first value of r is equal to 0. Next, A is equal to 4q plus 1. In this expression, we are substituting the value A is equal to B the value 4. Q is equal to q plus 0. 4q plus 1. A is equal to 4q plus 2. A is equal to 4q plus 3. The question it is specified as A is a odd positive integer. So we can represent it as only A is equal to 4q plus 1 and A equal to 4q plus 2 because these two numbers generate it as even numbers and these numbers are odd numbers. Hence the solution is proved. We can say that any odd integer is of the form 4q plus 1 or 4q plus 3. Once again, the question is show that any positive odd integer is of the form 4q plus 1 or 4q plus 3 where q is some integer. Here the solution, consider A as a positive odd integer. According to Euclids theorem, A is equal to bq plus r and the value of b is equal to 4. Remainder values lies between 0 and 4. Remainder can take values 0, 1, 2, 3. Hence, by using these values, we can represent this theorem as A is equal to 4q where the value of r is equal to 0, A equal to 4q plus 1 where the value of remainder is 1, etc. A is equal to 4q plus 2, A equal to 4q plus 3. Here we specified as A is a odd positive integer. So A can take only values equal to 4q plus 1 and equal to 4q plus 3 because the other two numbers is represented as in form of even number. Hence the solution is proved. Another example specified in the textbook is a sweet seller has 420 kaju burfis. 420 kaju burfis. And 130 badam burfis. She wants to stack them in such a way that each stack has the same number and they take up the least area of the tray. 420 and 320 are the numerical values. What is the maximum number of burfis that can be placed in each stack for this purpose? For questions like this, that is maximum values like that, we have to use Euclid's theorem to find out HCF. We have to find out the HCF of these two numbers 420 and 320. We show it here and the result we get it as 10. So the maximum number of burfis that can be placed in each stack is 10. So today we discuss about Euclid's theorem, Euclid's division lemma, and some of its solutions are discussed, some of the problems are discussed, and Euclid's division lemma. Here the application we discussed in Euclid's division lemma is how to find out HCF in simple method. Here we discuss about the theorem and some of its problems and some proofs related to Euclid's division lemma. Okay. Thank you.